And there will be announcements to all of these on Canvas, so you don't have to worry about writing everything down. Yes?
Do you have suggestions for the sigma range?
So yes, that was a question posted on Canvas, and I think someone answered it. Think of it just like, so sigma square behaves a lot like C. So you might want to think of similar sort of C that worked in the previous thing, and you should make that the sigma square. Okay?
How many epochs is too many epochs?
Good question. How many epochs is too many epochs? Are you plotting the learning curve?
No, but I should do that.
You should do that. Because if you're plotting the learning curve, you will see that after a point there's no change in objective. So really the right way of tracking when to stop is to keep track of the objective value. And if the objective does not change between epochs, then you know that you're just wasting cycles. Okay. That's one way of doing it. Another way of doing it is, just fix it to 10 or 20 or but that's a less formal thing. What you should do is track the objective. In fact, if most learning packages that actually solve these kinds of optimization have some epsilon as part of the, that's set and baked into the code, and if the objective change is within that epsilon, they say that it's not learning anything, so they stop. And you have to be careful about it, whether it's relative change or absolute, because that might make it. Speak up.
So when calculating the objective function, you just use a random example.
No. The objective function is on the entire training set.
The
function that you are actually trying to minimize, what you care about. Yeah.
You need computer intensity sum over all 3000.
Yes, and that's why you try to do it only at the end of each epoch. So an epoch is simply one iteration over the training set, and then you compute the objective, that's another iteration over the training set.
So in the homework it says to report the negative of the log likelihood.
Yes.
Is that pretty much our weight vector then?
No, the negative of the log likelihood is the objective.
Okay.
It's the function you're trying to minimize.
Okay.
The weight vector is just the vector. The negative log likelihood is the objective function for logistic regression, the function that you are trying to minimize. And the reason reporting that makes sense is because you're trying to minimize it, and you can check. In fact, one of the best ways of tracking errors is actually to plot the objective function, negative log likelihood or the SVM objective or something. Because if you're minimizing the objective, and it seems like at the end of every epoch it's going up, you know there's a problem. So that's actually the reason why I asked you to plot
it. I knew I needed to ask a question, I can't remember for sure. So the learning rate for stochastic gradient descent, should we just use something that's square summable?
Yeah. There's some discussion on the...
Yeah, I was the one that posted on.
Yes.
Okay.
And actually there was a reasonable suggestion at the end of that.
Okay.
So think of it as very similar to what we had for SVM. The requirements are the same. It should be square summable but not summable and okay. In fact, the stuff that you use for SVM might just as well work. You have to be careful about what we had a C there, and here there's a 1 over sigma square. But C and sigma square are actually like each other, so you have to do some translation. The reason I have been definitely less specific in this homework is because you've done this a few times. So I now want you to explore the space of ideas, mostly to keep you interested.
I do have one more question, I just remembered. For the negative log likelihood, should we calculate that for the entire...
Right, I just answered that. You have to do that at the end. You have to calculate the negative log likelihood over the entire training set at the end of that, because that's the function you care about very much. Other questions? Yes.
I'm getting some overflows in my exponential
Ah,
Yeah, I am too.
with the non-scaled data, but I'm not with the scaled data.
yes.
So I guess, do you have some suggestions on what hyperparameters to use?
So,
Because
one of the problems with these kinds of models is that you will get exponential overflows, and you have to be careful about how you compute these values. And one way of doing that is if you're computing e power, so you after a certain value of, so you want to compute, let's just write this down. You want to compute log of 1 plus e power something, let's call that z.
Yeah.
Right? Now, when z is very high, this is roughly equal to what?
Minus.
0. When z is very low, this is roughly equal to z.
what about when z is very large negative?
When z is very large negative, then, so basically what you do is this function looks like this. After a point, you pretend you just make it linear. You set a threshold, and it's an approximation.
Right, but the derivative of that is not log, right?
Yeah, but why? When does the
With your update.
with your updates? Yes. So even with updates, you have to do some hacks of this kind. Let's have. Can you start a thread on the discussion board, because I'd like to actually get to EM today. But this is a bit of a hack that is sometimes needed on certain data sets. As you point out, I mean, scale might not need it, but the other one might. So you have to, there's some messy programming stuff to do that.
I was thinking just change your hyperparameters, have like scale.
Yeah, you could do, that could be doable, but perhaps the best hyperparameters are the ones that are not numerically supported. So, let's have a discussion. Other questions? Yes?
Oh, can I say this one directly equal to 3 minus 3? I mean, because even z is small, it's also small, close to 0.
Yeah, but this region is where it's different. When it's between a certain range, it's actually not linear. After a point, it can be approximated as linear, but in some ranges, it's not. So my recommendation would be, before you start doing any approximations, see if the actual thing works. And if it does, then why bother with approximations? Other questions? Okay, so just a quick reminder of the announcements. Final exam next Wednesday in class, closed book. It's at 1 o'clock, not the usual time, just keep that in mind. There will be extra review sessions. There's some sample questions for the final that's posted. There's a project that's due at the end of next week, and there's a homework due on Thursday, so you can't blame me for not keeping you busy. Alright, so we are still talking about expectation maximization, and I'm not going to go over the derivation of this whole thing, and instead talk about the actual algorithm and try to derive, instantiate EM for a particular family of probabilistic points. So the setting is, we have examples, but we don't have labels, and we would like to somehow impute or infer labels for these examples. We probably have zero, in the worst case we have zero labeled data. Just because we have zero labeled examples doesn't mean we can't write down an objective for maximum likelihood. We can always try to maximize or try to find parameters that maximize the likelihood of the data being generated. Here LL is just shorthand, and this is very often used in books and papers. LL is just a log likelihood. We're maximizing likelihood, which is the same as maximizing log likelihood, and what we want is to maximize this sum of log of sum, and yi is the label. And at the end of the last lecture, and I hope you actually went through the slides and worked out the math. What we did was to show that the log likelihood of the data, here PQ alpha is just summarized into a theta. The log likelihood of the data given the parameters is always upper bounded, greater than or equal to, sorry, is always greater than this function, which is the expected log likelihood minus some kind of constant which is independent of theta. And this is true for all values. So what we have is LL of data given the parameters is greater than or equal to this script L of, this is true for all Q. And Q is some probability distribution over the labels. I mean some distribution over the labels for each example. So for any choice of Q, this property holds. So what we will do is now, instead of maximizing the function that we care about, we will set up a series of optimization problems of the script L kind, this kind, and repeatedly optimize that, and with the hope that we will get to a good value for theta. And I'll show you we will work out this detail, the details of it. So what we would like now is, what we plan to do is to repeatedly maximize functions of this kind for different choices of Q, with the hope that at the end, the theta that maximizes this function is a good enough theta for the original log likelihood of the data. We still need to find some way of, so this is true for all choices of Q. We still need to figure out what's a good choice of Q, and it turns out, and I have details in there if you're interested, but it turns out one of the best choices of Q is to simply pretend that the previous parameters that we have, the previous probabilities that we have, are the true model. And we can say the distribution of labels for a new example. So remember, for each example xi in our training set, the setting we have is, we have examples xi. We don't have any labels. We would like to get some function that can predict the label y for a given example. So what we'll do is pretend that our current estimate of the parameters, the theta, which for example in the naive base it would be the priors and the likelihoods, some function that we have, some parameters that we have are the ground truth, or are the best guess that we have, and use the probabilities according to that current model as these functions Q. Questions before we move on? So I'll go through the actual general recipe for constructing an EM algorithm before, and then you can come up with questions. So we want to come up with some parameters. What we'll do is take a guess for the parameters, and we repeat. The first step in the iterative process is called the E step. The name of the algorithm is expectation maximization. So this is the expectation step. The E step says, using your current parameters, using current theta, for every example in your training set, estimate the probability that this example will have a certain label. You know, if you have a model, this is simply prediction, right? This is just saying what's the label for an example given a current model. Instead of asking what's the label, we are asking what is the probability that the label takes a certain value. That's your Q. Now, given the labels, now you have something that looks like fully labeled data. We're going to now set up a new maximization problem. So that's the M step. So this is the M step of EM, where given the current values of Q, maximize this function, which is the expected log likelihood of data. You keep doing this many, many times, and when you get bored, you return the last value of data that you have. Before we move ahead, I'll let you stare at this and come come up with questions. Yes,
How you pick the initial parameter?
you take a guess.
Okay.
You pick randomly. I mean, in the absence of any other information, you just pick randomly, and sometimes it may not be good enough. This function is no longer convex. The function that we care about optimizing is not convex, so really the best we can hope for the final data is it takes you to a local maximum.
How many parameters do we choose?
Oh, so the theta here is completely decided by the probabilistic model that you've chosen.
Okay.
If you have naive Bayes, then, and you have say 10 features, and it's a binary problem, and you have Bernoulli, then you will have 21 parameters. And I'll let you convince yourself that that is correct. It depends on the model that, this is, like I said, EM is a meta algorithm. It's a recipe for generating algorithms. To instantiate it, you need to pick a probabilistic model. You need to make an assumption that your data comes from a certain model, and then all the other pieces actually fall into place.
Okay, so this M step here, where you're maximizing it, have we discussed how we do that yet?
We haven't. In fact, if we are lucky, the M step can be solved analytically, like naive Bayes. If we are unlucky, we just run another optimization problem.
So you said that this achieves a local maximum, which means that the initial starting place is
Crucial.
very important.
Yes.
Could you use some other mechanisms to kind of cheaply?
Yeah, in
Yeah,
fact, that
good
is
initial
often
guess.
done. That's quite often done. The best, or one of the best ways of doing that is to label a few examples. If you label 5, you get a lousy model, but at least you will be in the right ballpark. Other questions? And we'll see multiple versions of this, so if you have questions and you're feeling shy, there will be more other opportunities for questions. So let's talk about this expected log likelihood function. First of all, the second term is independent of theta, and there's no need to carry that around. Let's get rid of that. So the n step is simply to maximize with respect to theta the expected log likelihood according to the current model. Intuitively, the E step is asking, I have a model. What's the current distribution over the labels according to my current model? The M step says, using the current estimate for the the missing labels, what's the best model you can come up with? And you keep iterating these two steps. You hallucinate some parameters, you use that to come up with some labels. You use these hallucinated labels to refine your model, and somehow, magically, at the end, this converges. But it only converges to the local maximum, which is why, the initialization, the hallucination that you start off with is important. Okay, couple of other things. Just to make sure that you know this. If you have your current values of the parameters at theta t, you can compute the E step is done or is easy to solve. Why? Can you compute P of y given xi comma theta if I know theta and x? It's map prediction. It's exactly map prediction. Except you're not predicting a label, but you're predicting the distribution. It is map prediction. And for the M step, well, to answer the question that was asked, this can either be solved analytically, or you need to write down some optimization procedure to solve this. So let me just, if the algebra is too messy, let's look at a proof by pictures. So we have some function that we care about maximizing. That function is not convex, which means there are multiple maxima. In a perfect world, we would like to get here. Okay? So in EM, what you do is you start off with some random guess. Let's call that theta 0. And using theta 0 is the probability distribution. Remember, theta is always defining the probability distribution. Using the current parameters, you construct a new optimization problem. And there are two important properties of this new optimization problem. Actually, three. The first one, the new problem is convex, or actually it's concave here. We are maximizing. The new problem is concave, which means there's a unique maximum. The second one, the new problem is always below the new function that you care about maximizing is always below the original one, which means you'll never really overshoot. You'll not make egregiously wrong mistakes. And the third point is that this approximation, the way we constructed this function, our choice of this q, basically means at the point that we are at theta 0, it touches the original function. The new function touches the original function and is always below and is concave.
So I'm looking at this picture and I'm thinking that it would be absolutely wonderful and perfect world if we had that blue line, but we probably don't.
We
So-
don't have the blue line, but we have the blue function.
Oh, we do?
Yeah, that's the function. That's the original.
So is there some way we could see where the global maximum may lie?
Oh, that's nice in one dimensions, but we are talking about thousands of parameters.
Okay.
So in one dimensions, you can eyeball it and hopefully get an answer.
Okay.
If you're talking about a 1,000-dimensional space, there's no way of actually solving this.
So might it be wise to pick different theta naught?
Actually, that's a very common strategy. You use random restarts. You try multiple theta zeros, run EM, pick the one. So maybe the first one takes you here, the second one takes you here, the third one takes you here, the fourth one takes you here. After 10 trials, you pick the highest objective that you ever got and hope that that's the best you have. You had a question?
So with this example of a function, we could still do gradient us in this case,
Actually,
right?
that's another interesting.
On the original function, blue function, you still get a local maximum.
Yeah, that's actually a good point. And in fact, gradient ascent might still work, and in fact, it's commonly used for many non-convex optimization, especially in the deep learning kind of universe. This can be seen as a variant of that. This belongs to a general family of algorithms called majorization, minimization, as I meant was I telling you? Yeah. And this has better guarantees, but not necessarily this. It has the same flavor. You could just climb a hill. You might start off here and you climb a hill, or here and climb this way. So yes. But just to continue on this, you built an approximation, and now you have this curve, which is your expected log likelihood. You try to find its maximum, and that gives you a new set of parameters. Now you have a new set of parameters. New parameters are just like the old. I mean, it's a collection of numbers or probabilities. You set up a new problem based on the new parameter. This new problem has the same properties. It's concave, it's always below the original function, and it touches the original function at theta 1. So you get to its maximum, you set up a new problem, you get to its maximum, and keep going. Hopefully, you'll get here.
How do you know this always going to fall underneath the original curve?
That's the proof that we had last week. That's basically a byproduct of Jensen's inequality. And in fact, that's required to make this work. In fact, I very strongly encourage you, given this kind of picture, just go over the proof and see what it means. Because this kind of highlights what we are doing. So, a couple of things. First, the initial guess is important. Clearly, in this picture, I started off in a nice place and we went to the peak, but you could start off in the wrong basin or hill and end up at a lousy function or a not so good function, and that happens very often. And especially when the problems that we are training get larger, that happens more and more often. Because the optimization, the objective function, this blue curve, can be very, very spiky and very bumpy. So a random chance will not necessarily take us to the best possible region. The way I like to think about the EM algorithm is we have a difficult optimization problem. One that does not necessarily come with a lot of guarantees. And instead of trying to solve the difficult problem, we are replacing it with a series of easy problems, concave problems, that we know how to solve. And by constructing a series of easy problems and a theorem that says that at the end of the series of easy problems, you will get to the solution of the difficult one. We are kind of in good place, except the initialization matters. Okay? So other points, like I said, just to summarize, EM will converge to the maximum, local maximum, the log likelihood. There's a question of how many iterations, how many times should you do this outer loop? And the answer is exactly the same as I've been giving for other optimization. You do that till you converge, meaning you have to keep track of the objective. And the final thing is we still need, this is a meta algorithm. This is just a general recipe which works for any probability distribution, any probabilistic model. We still need to specify what's the probabilistic model that applies for your task. And that will give you your own set of thetas. And then now you have to also solve, the second thing that you need to do is figure out a way of solving the maximization problem. So, before actually instantiating this, are there questions about general recipe that is EM? Yes.
So if we know some parameters on the parameters, it shouldn't be hard to extend it to the map, right?
If you
This is an ML.
So this is maximum likelihood if you have some prior on the, yeah, I don't think it should be particularly hard. Yeah, I know, it might actually work out. Yeah. But I have to actually write it down to see if it works. Other questions? So we have a recipe for building algorithms. Let's actually try to instantiate to a problem that we've seen. We're still trying to, just to remind you, we are trying to learn when we don't have any labeled data. And we started looking at the 3 coins example, and there were these two, we considered many scenarios. 2 of them were actually easy, and we knew how to solve them. The first one is if you know the biases of the coins. So this game is, we have 3 coins, 0, 1 and 2. 0 has the probability of getting heads, that's alpha. 1 and 2 have P and Q probabilities of getting heads. And if you knew alpha, P, Q, and if I tell you that the coin was, what is this, coin Z, right, if the coin, there's something wrong here. So if you knew alpha, P, Q, and if I tell you that the subsequent tosses, so the game we played was first I tossed coin 0, if it was heads, then I tossed coin 1 4 times, if it was tails, I tossed coin 2 4 times, and I only show you the last 4 tosses, and then I ask you, was coin 1, did coin 0 show heads or tails? And if you knew the biases of the coins, estimating whether coin 0 showed heads or tails is easy. It's exactly map prediction. So that's basically saying, given your model and your features, can you get me a label? We know how to do that. Scenario 2 was, if you had complete data, examples of the form, here is the value of coin 0's toss and here are the subsequent 4 tosses, and many such examples, then you can estimate biases of all the coins. The difficult situation was scenario 3, when I hid what coin 0 said and only showed you blocks of 4 tosses and don't tell you whether the second set of tosses come from coin 1 or 2. To answer that, we looked at, in grand tradition, instead of solving the problem we have, we tried to solve all problems of this kind, and that gives us this EM algorithm. Still, we need to instantiate it for this specific case of the 3 coins. So let's do that. So we have 3 coins, coins 0, 1 and 2, and like I said, the scenario is you toss coin 0 first. If 0 says heads, you toss 1 4 times. If it says tails, you toss 2 4 times, and you only see these observations. I don't know whether these blocks came from 1 or 2. And now my goal is to estimate alpha, p and q using these numbers. So xi is just one of these examples, a vector of size 4, and yi is, for that particular xi, did coin 0 show heads or tails. And the model we have, according to this, according to the assumption on top, is the probability of xy. If I had alpha, p and q, the probability of x and y is simply if the y is coin 0. If coin 0 said heads, you can say heads with probability alpha. If there are k heads here, so k equals 3 here, and k, in the first one k equals 2 here, 3 and 2. If there are k heads, then you just count p power k, 1 minus p power 4 minus k for the first case. Or in the second case, it is just 1 minus alpha because coin 0 was tails here, and you are tossing coin 2 4 times, so it is q power k, 1 minus q power 4 minus k. It's just a collection of Bernoulli. Okay? Yes?
Is this the generative model for the observations?
It's exactly the generative model. That's a good point. This is the generative model for the observation. This simply says, here is how the data was generated. First you toss coin 0, and then you toss coin 1, and the probabilities are defined to be the following. This slide entirely defines the generative model. Did you have a question?
Oh, no, I was.
Okay. And now we want to use this EM algorithm. Just I'm flashing this just to remind you. We have an E step and an M step to somehow use the data that we have to figure out the alphas, p and q. So to solve this, we need to first solve the E step and then the M step. That's it. All you have to do is solve the E and the M step, and the rest of the algorithm is easy. But that's like saying, all you have to do is write down the algorithm. But the E step is given a current model. If I knew that the biases of the coins were, say, alpha bar, p bar, and q bar, I can ask, what's the probability that a particular set of instances came from coin 0? So, in the notation that we had before, this was theta, and we are asking what is p of y given x comma theta. Okay, so we care about, or in fact, let's say what is p of y equals heads given x comma theta. By Bayes' rule, we know that that's proportional to just the likelihood and the prior. And if you have k heads and 4 minus k tails, just saw this, we can write down what's the probability, or I'm going to define this quantity, the p of x, the probability that a particular set of examples came from coin 0 being heads. Let's call that CIH. The ith example, the probability that the ith example corresponded to a heads for coin 0. Let's call that CIH. And CIH is proportional to this quantity, and with just some little bit of algebra, I can write down the value of CIH. If I knew my current parameters, this is exactly maximum a posteriori probability. This is the likelihood and the prior, and this denominator just normalizes things so that it adds up to 1. Before I move ahead, are there questions? Yes?
Here xi is 4 tosses. right?
Xi is, so this could be x,
Right.
x1,
Yeah.
4 tosses. So what we have done here really is we've solved the step. All I do is ask, given your current model, what's the probability that the label is some value for a particular example? That's this quantity here. So this is pretty much it for the E-step. The E-step can almost always, in fact, very, very often, the E-step can be just computed on paper for most models that you'll probably see at least for the next 2 months, or 5 months, let's say. There are certain models where even the E-step cannot be done on paper, but let's not worry about that for now. So the E-step is simply asking what's the probability that the output is a certain takes a certain value. In this case, the y is heads for a particular example. If I knew that the probabilities, the current parameters are theta, are known to, are fixed. Okay, so that takes care of the E-step, and really, remember that Q that we had in the EM algorithm, the distribution over the labels, it turns out that's exactly P of y given x. And that's by definition what we call C. CIH is simply asking what's the probability that the ith example corresponded to a heads in the first, as the heads as a label. So now what we have is an estimate of Q for every training example if we had current model. So now we can look at the M step. But before that, any questions? Okay, so for the M step, we care about maximizing this quantity. Let's simplify this. Let's look at the term inside the expectation. That's the log likelihood of the data. The log likelihood of the data is exactly fixed by the generator model. Just asking what's the probability of observing a certain fully labeled example, XY pair. Right? If I knew that given the current parameters, this is the log likelihood of data, this is just from one of the previous slides. Or actually this is the likelihood. The log likelihood is just taking the log, and I wrote it down mostly to point out that even in the simplest of examples, you can have like a number of symbols on your sheet of paper can just blow up when you are deriving here. So I've just taken the log of this. Okay? So what we have is we have some way of writing down this function, log p of y, log p of xy. Now let's try to use that to expand the expectation. This is simply, by definition, it is given a current q, q can either be heads or tails. So it's either q of heads times this value inside it, plus tails times this value inside it. So this is just the definition, E of x times x. Just so happens that instead of p, it's a q. So right, I've just expanded this. So I can either be heads or tails. So you have two terms to this expectation. I'm going to argue that the problem is basically solved here. unless somebody disagrees. Is the problem solved? Have we finished everything?
We still have to maximize, right?
We still have to maximize, but are the pieces of this function known? What's q of h?
That's the C.
That's the c. Q is just the c. Q is simply asking, we remember that we had q of x is p of, or q of y actually, sorry. Which we just, because I didn't want to write this multiple times, I call this the I of y. So q is just the c, and the log likelihood is literally just coming from the definition of the generative model. So what we have done here is the c in the blue is just a constant. The log likelihood can be written down in terms of all the alphas, p's in the q, and what you will end up if you substitute is enough math to cover the white one. So which means you're going to do it, not me. But I assure you it's just very, very simple algebra. It might be, after one iteration of doing this, you'll probably get bored. But it's probably worth explicitly working out the details of this, because it takes a few, EM is one of those algorithms where the first few times you instantiate this hyper or meta algorithm, instantiate this recipe, it seems like such a mess. So many symbols all over the place. But afterwards you start noticing the patterns, and sometimes you can just, even without writing down the objective, you can write down the answer, because there's a common pattern that shows up in many across multiple models. So what we care about, maximizing this function, is the same as maximizing this function in terms of p, q and alpha. And of course you're going to do it right after class, because you need to. The good news is the answer looks like this. Turns out, if I had values of the c, and we have values of the c, if I knew the previous estimate of the parameters, I have values of the c. It turns out the alpha looks like just sum over c divided by number of examples. P is another term, but there's a very intuitive explanation. If I thought of the c, instead of c was, what was c? C was just the probability that the ith example had a label heads. Instead of thinking of it as probability, if I thought of it as an indicator that the ith example was heads, meaning it's either 0 or 1, then this quantity here, sum over c I, is just counting the number of heads. Right? If c was a function that said 1 whenever it was heads and 0 whenever it was tails, summing over all the c's just gives you the number of heads. It turns out that instead of actual counts, we have soft counts. And actually the same intuition carries for the p's and the q as well. So effectively the EM algorithm is treating these expected values of labels as soft counts. Question?
What is K of?
What is K? K is the number of heads. I introduced that like way back, but yeah, K is the number of heads in an example. So in fact, this one says, among all the examples that had heads, how many of them, among all examples where the first coin 0 had heads, how many of them had how many heads were seen in the remaining 4? So if you have, so let's say if C was, let's say this was heads, tails, heads and heads, suppose, meaning suppose these were actually, instead of soft counts, these were actual hard counts. The numerator here is simply asking, it's counting 3 plus 3 plus 2. Among the examples that are labeled heads for coin 0, how many coin 1 heads were seen? That's the numerator. So really it's this term here is asking number of heads for coin 1 divided by number of tosses of coin 1. And that's the bias of coin 1. Intuitively, if you had the labels, that's how you would estimate it, right? The bias of coin 1 is number of times you see a heads for coin 1 divided by number of times you toss coin 1. Same thing for coin 2, except we don't have the actual number, instead we have these soft counts. Okay, so are there questions about this? Yes.
I was just going to make a general comment. Maybe I'm actually, when I was working through the homework, one of the gotchas is when you get to that point where you have to maximize, it's tempting to plug in the expression for C, like in this case.
Right.
But you want to keep that fixed.
Yes.
And maximize.
In fact, that's actually why I introduced this. That's a good point, and it's a common cause for
Otherwise,
grief.
it's really complicated to maximize.
Yes, and it's a very common cause for grief. Remember that we want to maximize a function that looks like this, like this here. But this C itself was probability of y given xi comma alpha t minus 1, or let's just call it alpha bar. Which is, we had the value for this. This is some giant alpha times p power k. I'm just going to write this mostly to scare you. Divided by some this plus similar thing with q's. It's just a nasty term, but it's all p bar and q bar, which means as far as this maximization is concerned, it's just a number. It's not something that can change. Changing the value of p, q and alpha will not change the value of c, because c uses the previous values of alpha, p and q. You had some estimates of all the parameters that you computed yesterday, and you don't want to change it. Today, it's a new day, this epoch, and you're trying to find the best value of alpha, p and q, but what you did before does not change. And this is a very common cause for grief, and if you somehow end up missing that, or you drop a bar or a hat or a t minus 1, you'll end up with a function that's rather nasty. So for the homework, it turns out if you do the right thing, the solution actually should be easy, right? If it seems like the homework is really painful, chances are you're kind of walking down some path that is not optimally the one that you should be.
We're just writing down an algorithm.
Well, you also have to, you are writing down the EM algorithm, but you have to talk about how do you maximize this.
You're not actually programming something.
No, it's analytical. There is no programming there. It just works out completely on paper. There's one parameter, right? In the homework, it's a Poisson distribution with one parameter, if I'm not wrong. Or two.
You got a probability of being in one group, and each group has a different.
Right, so there's one lambda for each group.
Yeah.
Or one lambda for each, was it Target and Walmart or some stores, I don't remember. Each label, one lambda. So there are two parameters, and you can write down the optimization, the M step, as it has a clean solution.
Well, I would say there's three because of the eta, that's the...
Right, there's the eta, yes, there's the prior distribution of the label. So there are three numbers. It's just like this actually, it's just like alpha PQ, you have, eta, lambda 1 and lambda 2 or something. Alright, so I'm going to rush through EM for naive Bayes mostly because I want to get to k-means. You can do EM for naive Bayes, and the setting for EM for naive Bayes is actually a rather intuitive one. Remember that we were talking about document classification for, let's say you want to build a spam detector and you have emails It's just that nobody bothered to give you labels for whether the email is spam or not. So all you have is a big bucket of emails. And now someone comes to you and says, build a spam detector for me. Use these features. And use naive Bayes. So the first step that you need to do to instantiate EM is to write down the generative model. You need to somehow say, how is a complete labeled example generated? In other words, you need to talk about what's the problem. You need to come up with a functional form for Pxy. Naive Bayes, we already know how to do that. It's P of y times the class conditional likelihoods, the product of the class conditional likelihoods. And in one of the earlier lectures, we saw that for this particular case, we can assume that we have these prior of the label can, let's call it P, and the likelihood of each feature can be, let's call it A, J and Bj. So theta, the set of parameters that we need to learn, is this collection of all the numbers that we need to find. Because if I knew these numbers, I can completely write down the probability distribution for any particular example. So what we've just done is we've defined the generative model. Step 1 in creating an EM algorithm is to make an assumption. I assume that the data is created this way. So you write down the generative model. And this is how it's done. This is a simple model, but even in very, very complex models where you have priors on priors on priors, the same thing happens. Then you try to do the E step. The E step is asking, suppose I give you a value of theta, can you tell me what's the probability that the label takes a certain value? What's the probability that the label is 1 when, for a particular example, given a current estimate of theta? We know how to write this because the numerator of this term here, this thing here, is exactly what our generative model gives us. So we know how to compute everything in this function if I knew theta. Okay? This is just maximum a posteriori. This is just not even maximum a posteriori. This is just calculating the posterior probabilities. So because we have fixed a generative model, we can write down the posterior probabilities. So the E step very often just naturally comes out of the model that you have chosen.
Can you go back a slide?
Sure.
When we were talking about the coins, the model was a piecewise function that had one for the case of heads and one case where the label was tails.
Right.
Why don't we have a piecewise function here?
We have the same thing. When so think of this, one is heads. When y equals heads or 1, you use these coins, all the A's, to create the document. When y is tails, you use these coins, all the B's, to create the document. And now I've just given you documents and I'm asking, what's all the parameters? Right? So you have these, you have a choice at the top, and that decides which probability distribution is going to be chosen, either this one or this one. Okay, so the E step lets us calculate this whole thing, and the M step, typically I'm not going to do it because it's just a lot of math, and better you than me, as I say. The M step typically can be worked out by following a sequence of steps. First, you need to write down what is, I know my generative model. I know what is P of x, y given theta. Use that to write down what is log P of x, y given theta. In other words, just take log of your probability. The second thing you do is you write down the value of the expectation. This expectation here. So you write down, first step takes care of this, the second step takes care of this, where Q comes from the E step. Now you have a function. Now you have a function and you can maximize it. All you have to do is just take the derivative with respect to all the things that are not fixed and set them to 0, get an estimate. Again, you should work this out. This is, it's almost impossible to understand the EM algorithm unless you actually, work it out on paper. But again, like the last time, I can give you the answer. It turns out, just like we had for naive Bayes, in the fully supervised setting, in the unsupervised setting, naive Bayes looks like the EM algorithm gives us the following estimate of probabilities after the M step. In original version of naive Bayes, P, the prior, was how many times was 1 seen divided by how many times was, how many examples there were. The probability of seeing 1, of the label being 1, is just a fraction of 1. Instead of counting, we use soft counts. In other words, soft count is just the sum of probabilities of 1 happening. AJ, which is the probability that a particular feature is 1 when the label is 1, is simply the number of times you have the feature being 1 when the label is 1 divided by the number of times the label is 1. That's in the fully supervised setting. Now we are in the land of soft counts. So you replace all counts with sums of probabilities. It just so happens this emerges from taking the derivative and setting it to 0. And when we had fully labeled examples, we had counts. The whole thing was done with counts, and now it's just we have no way of counting because there are no labels. There's no labeled data. Instead, we keep the uncertainty alive, and we use soft counts. Effectively, what's going on is another way of interpreting this solution is that the probability behaves like an indicator function. The probability that the label becomes 1, for an example, behaves as if it's an indicator function. Actually, it's the other way around. Indicator can be seen as a probability. It's just all probability is on that label. The indicator that y equals 1 is simply this probability function that's peaked on that label. Here we are keeping the uncertainty alive. Questions? So, quick summary of EM. It's a general procedure. You often see this phrase EM algorithm. It's not an algorithm, it's a recipe for constructing algorithms because EM changes when you change the probabilistic model, when you change the generative model. So, I like to think of it as a recipe for writing down algorithms, and it's a family of algorithms that works for the case when you don't have labeled data. And the way we try to solve this is we construct a series of optimization problems that take us to the local maximum of the likelihood function. We looked at an example of how, I very briefly rushed through an example of how EM can be applied for Bernoulli functions. And a couple of general comments. As many of you noted, EM is often very, very sensitive to the initialization, and bad initialization is really hard to avoid. So one common strategy is to do random restarts. Instead of initializing once and climbing up the hill, you initialize 1,000 times, run it on 1,000 different machines. Pick the one that has the best objective value. Another thing that's important is quality of the algorithm, of course, depends on which generative model you use for the data. So very often, we hardly ever know what's the right model that generated the data because you're just given emails. How do you know that it was generated using naive Bayes, for example, for spam detection? So EM can be very sensitive to the choice of generative model. If you have the right model, then you might actually if you have the right generative story, then you might actually get good parameters. If you have the wrong generated story, then you are adding on errors on top of others. There is first the error that comes up because of initialization. You might just end up in the bad local maximum. Then there's on top of that, there's the error that comes because of the choice of models. Questions?
You put your generator model in cross validation.
It's often done, yes. You try out like 18 different models and you cross validate over all of them. But how do you cross validate? You don't have labeled data. What's an error here? So there's something to think about. Did you have a question?
If you have unlabeled data, would this be your like default algorithm of choice?
Yes and no. It depends on which. Some variant of this ends up being. There are many variants of EM, and typically some variant of this ends up being the default choice. The variants can come from. Sometimes I said the E step is often easy to calculate, right? Sometimes the denominator in the E step is over so many items that it can't be done. So that becomes a bit of a problem. So that might change my choice. The M step might be intractable. It's concave, but it might be a painful optimization problem. So that might also change how I. So those are the two things that often are the criteria that bias this choice. But that's a good question because that's going to take us to the last topic that we'll actually cover. But speaking of last topics, the syllabus for the class originally intended to cover multi-class classification and also dimensionality reduction, but clearly I'm not going to get to it in 20 minutes. So, and in the next lecture, I really do want to spend the next lecture talking about taking a step back. We've been knee deep in algorithms and math. I want to take a step back and talk about how we can apply these ideas on, I don't know, classifying fish. So this k-means is a variant of EM, and that will be really the last actual topic we'll cover. So in EM, at every step, and even this I'm going to just rush through because I want to give you an intuition of k-means and not necessarily the actual details. The E step in EM estimates what's the probability that a certain example takes a certain label. There's a variant of EM, a very popular variant of EM called hard EM. Hard EM says, instead of actually estimating the probability, just take the most probable label. Instead of maintaining soft counts, just pretend as if your previous model was actually the right model and pretend as if your previous model was an oracle that went around labeling examples. Use the labels and retrain your classifier. In other words, just don't keep the uncertainty alive. And the choice of whether you should do this versus not is an open question. It seems that some problems are better suited to hard EM, some data sets are better suited to hard EM, whereas some are better suited to soft or real EM. There are other variants of EM. Just a few that I found in a quick Google Scholar search. There's something called MCMC EM, Markov chain Monte Carlo EM. There's something called variational EM. There's something called generalized EM, which actually neatly combines the original EM and hard EM into one broader family of algorithms. But I'm going to quickly step through the instance of hard EM, mostly to tell you about a family of models that we have not seen before, a mixture of Gaussians, or it's also called the Gaussian mixture models. The generative model for this is, so examples in this space are, you have inputs which are d-dimensional vectors, and instead of two labels, let's say we have k labels, multi-class. And the generative model looks like this. First, you roll a k-sided die. You pick, which is the technical name for a k-sided die is a multinomial distribution. So you draw a label from multinomial distribution, which is, let's say you pick Li, you pick the ith label, and once you have that, each label corresponds to a normal distribution, and you sample from that normal distribution. That gives you a label and a point. That's your label, that's your point. This is the generative story. Now, having told you the generative story, you should be able to think about what is the probability of that point being generated. Let's look at a one-dimensional example. A mixture of Gaussians is simply, in this case, like a sum of 3 Gaussians. There are 3 labels, 1, 2 and 3. So, in order to generate an example, let's say, first I roll a 3-sided die and it picks this Gaussian. It picks L3. And then, using the normal distribution that corresponds to that Gaussian, you pick a random point, let's say it picks this point. So now you have an X and a Y pair, and that's how the data was generated. Similar thing you can talk about in 2-dimensional cases where you have a group of Gaussians and you pick one of them, you roll a die, pick one of them first, and then you you draw a sample from that Gaussian. So if I have a point whose label is X, let's say I have a point X whose label is Li, I can write down what's the likelihood of that point. Likelihood of the point is simply the probability that I chose the label times the probability that I choose the example for that label, which is just the multinomial times the Gaussian. Okay? This is just one a very commonly seen family of probabilistic models. The unsupervised version of this looks like this. Of this problem looks like follows. Now I give you a collection of points, and I tell you that these points were generated according to the mixture of Gaussian. But I don't give you any labels. I just give you a collection of points and ask you find the model that generated the data. So in other words, this is like the setting that I had in the beginning of the unsupervised. You have a collection of points, and now I ask you, learn. And if learning is, it's an impossible goal if you do not have an assumption about a model, and if this was a mixture of Gaussian, it will learn 2 Gaussians around this. But in the interest of time, I'm not going to talk about mixture of Gaussians. You can write down, you can go through the same series of steps that we did for EM. You can do the E step, where first of all, this is the complete generative model. Here I've assumed that all the labels are equally likely. Don't have to. You can do the E step. I'm going to really rush through these slides because I want to get to the example. You can ask, what is the probability that a label belongs to a particular point? That's your E step. This is given a collection of parameters. What's the probability that a particular point belongs to a label? And because it's, I know the mathematical or the algebra, the analytical or the functional form of these probabilities, I can write down, I can instantiate all these numbers, but it doesn't matter. Let's say that for a particular example, let's say this your current model gives this probability distribution over the labels. If you were doing the EM algorithm, what you would say is, it is this distribution, I'm going to preserve the uncertainty. I'm going to pretend that all these labels are possible. This label 5 is possible a lot. This one is highly unlikely, but I'm just going to keep that uncertainty to update my next model. In hard EM, what you're going to say is, let me just move all the probability mass into the one label that maximizes the probability, and just continue with EM. Meaning you believe the current model rather than keeping the uncertainty. That's your E step. So in hard EM, the difference between hard EM and soft EM is this tiny change in the E step. In real EM, you keep the uncertainty of the prediction according to your previous model. In hard EM, you just predict the label. Is the difference okay? The difference clear? And the rest of it just continues. So I'm going to step through this very quickly. It turns out that The whole thing is in the slide, so you can actually go through it and enjoy it in your own leisure. But I'm going to instead actually write all the algorithm. So you're given a collection of points, and very, very important, if I just give you a collection of points, there's nothing you can do because you need to still make an assumption. I think there are 37 labels in this problem, or I think there are 103 labels in this problem. I think there are 2 clusters in this problem. So you need to pick that number, k. Because this is Gaussian, selecting the initial parameters just requires mean and standard deviation of all those points. Let's assume that the standard deviations are all constant. So all you have to do is select a collection of the mean. These are all d-dimensional vectors. There are k such cluster centers. And you iterate. For every point, it turns out if you actually do the hard EM, what you do is the label for the point is simply the cluster center, the identity of the cluster center that is closest to that point. Every point gets a certain label. And then you just compute, iterate. You have a collection of points, and the first step here, what it said is point number 1 belongs to cluster 4, point number 2 belongs to cluster 3, and so on for all the m points. Now what you do is, for each label that you have, collect all the points that were assigned to it and take the average. That gives you your new parameters. This is your m step. This is your e. This part is your e step. This is your m step. And then at the end, you can either return the final model or return the final labels. Is this algorithm okay? Does this intuitively make sense? How many people have implemented this algorithm before? What is this? This is the k-means clustering algorithm. How many people have heard of k-means before? Way more. It turns out k-means is actually an instance of hard EM where you use Gaussian mixture models with uniform priors and constant standard deviations. A lot of assumptions packed in. So this is your k-means clustering algorithm. Those of you who have not seen k-means, here's a pictorial version of it. You're given a collection of points, and suppose k equals 3. You first take a random guess as to where you believe the cluster centers are, and those are these triangles here. I just randomly pick 3 points. Then for every point, you go around and say, this point belongs to this cluster center, this one belongs to this, simply because it's closest. This belongs to this because it's closer to this than this and this. And so on. So what you've done is effectively color every point according to the identity of the cluster center that's closest to that point. In the Euclidean sense, closest in the Euclidean sense. Now what you have is a collection of points with labels. Oh, this one is. Now you have a collection of points with labels, which means you can take their average. So just move the cluster centers to the average of the cluster. Okay? And now you have new cluster centers and erase the labels of the points again and try to re-estimate. Okay? And again, do the same thing. Recompute the means. So you have k means that you iteratively recompute. And you get a new set of cluster centers, and you color the points again. At this point you can stop or not. At this I have stopped because there's only so many slides that I can make. But this is basically the intuition behind your k-means. So just to quickly summarize, the k-means algorithm is an instance of hard EM. If this were not hard EM, I would not be assigning labels to all these circles. Instead, for every circle, I would have a probability distribution over the 3 labels. Question?
So for k-means, it looks like here, the means would stop moving because you're not adding any points.
Here, yes. After a certain setting, it converges, it just stops. Because after this, the label assignments will not change, which means the means will not change. So that's your convergence criteria. But that doesn't always have to happen. You can kind of, but in general, k-means also converges to a local maximum, so yes.
So for the soft EM, you would ultimately return your probability distribution, right?
Yes.
And then you just use that to predict.
Yes. It's very similar because here, instead of returning the labels, I could return the probability distribution, just the value of the means, and say a new point comes in.
That's basically like nearest neighbors after that?
Exactly. You just take the nearest mean. It's not nearest neighbors, it's just nearest mean. And you predict that.
What if you just did nearest neighbors, but then like calculated like, this is to me like.
It reminds you of nearest neighbors.
Yeah, what if you like did nearest neighbors, but then like instead of, if you just picked random means like in here, that's basically what this is, right?
But in nearest neighbors, you require label data. Right? So think of k-nearest neighbors. Your data comes with examples. If I just give you those blank circles that we had at the beginning, how do you do k-nearest neighbors? All you would say is when a new point comes in, it is closest to these 2 points. And k here is the number of neighbors, k nearest neighbors is the number of neighbors. Here it's the number of cluster centers. The connection is, in both cases, the Euclidean distance, or the distance, makes a difference. The Euclidean distance shows up in k-means because of the same reason the Euclidean distance shows up in least mean squares. It's at the exponent of the Gaussian, because we are assuming a Gaussian mixture model. It's just the math works out conveniently. Yes?
What can you do if you don't know how many clusters you have?
If you don't know how many clusters you have, there are 2 options. You guess and you hope it works. Option 1, and that's the most frequently done one. And option 2 is you can put a prior on top of that. If you don't know the number of clusters, I can change my generative model. First, instead of my generative model saying first I pick a cluster label and then using the cluster I draw from the Gaussian, what you do is first you pick a number of clusters and generate a collection of probability distributions for, in other words, you pick a number of clusters, k, and then generate a k-sided die, and then use the k-sided die to pick from the Gaussian. Roll the k-sided die to pick from the Gaussian. This is like a classic Bayesian trick. If you don't know something and you're not willing to commit to it, you put a prior on it.
I was gonna say, couldn't you like pick like a large number of clusters and combine like the like top?
Yeah, you do those kinds of things, definitely. In fact, clustering is one of those topics which there are way more algorithms than I can possibly ever cover in the -1 minutes that are left. But good news is that there's an entire semester worth of class on clustering next semester. So you feel that this is what draws you to machine learning, you should totally check it out. There are many such heuristics, and really one important question that shows up with clustering is, how do you even evaluate? I just come up with some coloring, who said this is correct? Alright, so let me wind up with a general comment about unsupervised learning. Unsupervised learning is a vast topic, and we barely even scratch the surface at this point. And the general theme is that you have examples, but you don't have labels, or you have many examples without labels, and maybe you have a small number with labels. That's called semi-supervised learning. A very popular strategy for unsupervised learning is some variant of the EM algorithm, where you hallucinate some parameters, use your hallucinated parameters to come up with an estimate of the labels, or maybe a distribution over the labels, and then use that to re-estimate your parameters and keep going around iteratively with the guarantee that at the end you will end up at a reasonable spot. Another name for unsupervised learning is clustering. Clustering is a large family of algorithms. We just saw k-means, and I introduced k-means mostly to point out that it's an interesting variant of EM. And it's an algorithm that is so easy to implement that pretty much it's often one of the first machine learning algorithms that a lot of people implement. In this class, of course, it's the last machine learning algorithm that we are seeing, but that doesn't mean much. Alright, so let's stop now and remember all those things, all the announcements I had in the beginning, extra reviews and all these things that are due. I have my office hours now, so I'll be happy to talk.